Linear functions. Imagine placing a plant in the ground one day and finding that it has doubled its height just a few days later. Although it may seem incredible, this can happen with certain types of bamboo species. These members of the grass family are the fastest growing plants in the world. One species of bamboo has been observed to grow nearly 1.5 inches every hour. In a 24-hour period, this bamboo plant grows about 36 inches, or an incredible 3 feet. A constant rate of change, such as the growth cycle of this bamboo plant, is a linear function. Recall from functions and function notation that a function is a relation that assigns to every element in the domain exactly one element in the range. Linear functions are a specific type of function that can be used to model many real-world applications, such as plant growth over time. In this chapter, we will explore linear functions, their graphs, and how to relate them to data. Just as with the growth of a bamboo plant, there are many situations that involve constant change over time. Consider, for example, the first commercial, the maglev train in the world, the Shanghai maglev train, Figure 1. It carries passengers comfortably for a 30-kilometer trip from the airport to the subway station in only 8 minutes. Suppose a maglev train travels a long distance and that the train maintains a constant speed of 83 meters per second for a period of time once it is 250 meters from the station. How can we analyze the train's distance from the station as a function of time? In this section, we will investigate a kind of function that is useful for this purpose and use it to investigate real-world situations, such as the train's distance from the station at a given point in time. Representing linear functions. The function describing the train's motion is a linear function, which is defined as a function with a constant rate of change, that is, a polynomial of degree 1. There are several ways to represent a linear function, including word form, function notation, tabular form, and graphical form. We will describe the train's motion as a function using each method. Representing a linear function in word form, let's begin by describing the linear function in words. For the train problem we just considered, the following word sentence may be used to describe the function relationship. The train's distance from the station is a function of time during which the train moves at a constant speed, plus the original distance from the station when it began moving at constant speed. The speed is the rate of change. Recall that at a rate of change is a measure of how quickly the dependent variable changes with respect to the independent variable. The rate of change for this example is constant, which means that it is the same for each input value. As the time input increases by 1 second, the corresponding distance output increases by 83 meters. The train began moving at this constant speed at a distance of 250 meters from the station. Representing a linear function in function notation. Another approach to representing linear function is by using function notation. One example of function notation is an equation written in the slope-intercept form of a line, where x is the input value, m is the rate of change, and b is the initial value of the dependent variable. Equation form, y equals mx plus b, function notation, f of x equals mx plus b. In the example of the train, we might use the notation d of t, in which the total distance d is a function of time t. The rate, m, is 83 meters per second, and the initial value of the dependent variable b is the original distance from the station, 250 meters. We can write a generalized equation to represent the motion of the train. d of t equals 83t plus 250. Representing a linear function in tabular form. A third method of representing a linear function is through the use of a table. The relationship between the distance from the station and the time is represented in Figure 2. From the table, we can see that the distance changes by 83 meters for every 1 second increase in time. Q&A. Can the input in the previous example be any real number? No. The input represents time, so while non-negative rational and irrational numbers are possible, negative real numbers are not possible for this example. The input consists of non-negative real numbers. Representing a linear function in graphical form. Another way to represent linear function is visually, using a graph. We can use the function relationship from above, d of t equals 83t plus 250, to draw a graph, represented in Figure 3. Notice the graph is a line. When we plot a linear function, the graph is always a line. The rate of change, which is constant, determines the slant or slope of the line, and the point at which the input value is 0 is the vertical intercept or y-intercept of the line. We can see from the graph that the y-intercept in the train example we just saw is 0, 250, and represents the distance of the train from the station when it began moving at a constant speed. Notice that the graph of the train example is restricted, but this is not always the case. Consider the graph of the function of the line f of x equals 2x plus 1. Ask yourself what numbers can be input to the function. In other words, what is the domain of the function? The domain is comprised of all real numbers because any number may be doubled and then have 1 added to the product. Linear function. A linear function is a function whose graph is a line. Linear functions can be written in the slope-intercept form of a line. f of x equals mx plus b, where b is the initial or starting value of the function when input x equals 0, and m is the constant rate of change or slope of the function. The y-intercept is at 0, b. Determining whether a linear function is increasing, decreasing, or constant. The linear function we used in the two previous examples increased over time, but not every linear function does. A linear function may be increasing, decreasing, or constant. For an increasing function, as with the train example, the output values increase as the input values increase. The graph of an increasing function has a positive slope. A line with a positive slope slants upward from left to right, as in figure 5a. For a decreasing function, the slope is negative. The output values decrease as the input values increase. A line with a negative slope slants downward from left to right, as in figure 5b. If the function is constant, the output values are the same for all input values, so the slope is 0. A line with a slope of 0 is horizontal, as in figure 5c. Increasing and decreasing functions. The slope determines if the function is an increasing linear function, a decreasing linear function, or a constant function. f of x equals mx plus b is an increasing function if m is greater than 0. f of x equals mx plus b is an decreasing function if m is less than 0. f of x equals mx plus b is a constant function if m equals 0. Interpreting slope as a rate of change. In the example we have seen so far, we have had the slope provided for us. However, we often need to calculate the slope given input and output values. Recall that given two values for the input, x1 and x2, and two corresponding values for the output, y1 and y2, which can be represented by a set of points, x1, y1, and x2, y2, we can calculate the slope m. M equals the change in output, rise, over the change in input, run, equals delta y over delta x, equals y2 minus y1 over x2 minus x1. Note in function notation two corresponding values for the output y1 and y2 for the function f. y1 equals f of x1 and y2 equals f of x2, so we could equivalently write m equals f of x2 minus f of x1 over x2 minus x1. Figure 6 indicates how the slope of the line between the points x1, y1, and x2, y2 is calculated. Recall that the slope measures steepness or slant. The greater the absolute value of the slope, the steeper the line is. Modeling with linear functions. Emily is a college student who plans to spend a summer in Seattle. She has saved $3,500 for her trip and anticipates spending $400 each week on rent, food, and activities. How can we write a linear model to represent her situation? What would be the x-intercept, and what can she learn from it? To answer these and related questions, we can write a model using a linear function. Models such as this one can be extremely useful for analyzing relationships and making predictions based on those relationships. In this section, we will explore examples of linear function models. Building linear models from verbal descriptions. When building linear models to solve problems involving quantities with a constant rate of change, we typically follow the same problem. Strategies that we would use for any type of function. Let's briefly review them. 1. Identify changing quantities and then define descriptive variables to represent those quantities. When appropriate, sketch a picture or define a coordinate system. 2. Carefully read the problem to identify important information. Look for information that provides value for the variables or values for parts of the functional model, such as slope and initial value. 3. Carefully read the problem to determine what are we trying to find, identify, solve, or interpret. 4. Identify a solution pathway from the provided information to what we are trying to find. Often this will involve checking and tracking units, building a table, or even finding a formula for the function being used to model the problem. 5. When needed, write a formula for the function. 6. Solve or evaluate the function using the formula. 7. Reflect on whether your answer is reasonable for the given situation and whether it makes sense mathematically. And 8. Clearly convey your result using appropriate units and answer in full sentences when necessary. Now let's take a look at the student in Seattle. In her situation, there are two changing quantities, time and money. The amount of money she has remaining while on vacation depends on how long she stays. We can use this information to define our variables, including units. Output, M, money remaining in dollars, and input, T, time in weeks. So the amount of money remaining depends on the number of weeks, M of T. We can also identify the initial value and the rate of change. Initial value. She saved $3,500, so $3,500 is the initial value for M. Rate of change, she anticipates spending $400 each week, so negative $400 per week is the rate of change or slope. Notice that the unit of dollars per week matches the unit of our output variable divided by our input variable. Also, because the slope is negative, the linear function is decreasing. This should make sense because she is spending money each week. The rate of change is constant, so we can start with the linear model M of t equals mt plus b. Then we can substitute the intercept and slope provided. M of t equals mt plus b. M of t equals negative 400t plus 3500. And to find the x-intercept, we set the output to 0 and solve for the input. 0 equals negative 400t plus 3500, t equals 8.75. The x-intercept is 8.75 weeks because this represents the input value when the output value will be 0. We could say that Emily will have no money left after 8.75 weeks. When modeling any real-life scenario with functions, there is typically a limited domain over which the model will be valid. Almost no trend continues indefinitely, and here the domain refers to the number of weeks. In this case, it doesn't make sense to talk about input values less than 0. A negative input could refer to a number of weeks before she saved $3,500, but the scenario discussed poses the question once she saved $3,500 because this is when her trip and subsequent spending starts. It is also likely that this model is not valid after the x-intercept unless Emily will use a credit card and goes into debt. The domain represents the set of input values, so the reasonable domain for this function is 0 less than or equal to t less than or equal to 8.75. In the above example, we were given a written description of the situation. We followed the steps of modeling a problem to analyze the information. However, the information provided may not always be the same. Sometimes we might be provided with an intercept. Other times we might be provided with an output value, and we must be careful to analyze the information we are given and use it appropriately to build a linear model. Using a given intercept to build a model, some real-world problems provide the y-intercept, which is the constant or initial value. Once the y-intercept is known, the x-intercept can be calculated. Suppose, for example, that Hannah plans to pay off a no-interest loan from her parents. Her loan balance is $1,000. She plans to pay $250 per month until her balance is $0. The y-intercept is the initial amount of her debt, or $1,000. The rate of change, or slope, is negative $250 per month, and we can use the slope-intercept form and the given information to develop a linear model. f of x equals mx plus b equals negative 250x plus 1,000. Now we can set the function equal to 0 and solve for x to find the x-intercept. The x-intercept is the number of months it takes her to reach a balance of $0. The x-intercept is 4 months, so it will take Hannah 4 months to pay off her loan. Using a given input and output to build a model. Many real-world applications are not as direct as the ones we just considered. Instead, they require us to identify some aspect of a linear function. We might sometimes instead be asked to evaluate the linear model at a given input or set the equation of the linear model equal to a specified output. Using a diagram to model a problem. It is useful for many real-world applications to draw a picture to gain a sense of how the variables representing the input and output may be used to answer a question. To draw the picture, first consider what the problem is asking for, then determine the input and the output. The diagram should relate the variables, and often geometrical shapes or figures are drawn. Distances are often traced out, and if a right triangle is sketched, the Pythagorean theorem relates the sides. If a rectangle is sketched, labeling width and height is helpful. Modeling a set of data with linear functions. Real-world solutions, including 2 or more linear functions, may be modeled with a system of linear equations. Remember, when solving a system of linear equations, we are looking for points the 2 lines have in common. Typically, there are 3 types of answers possible, as shown in Figure 5. How to. Given a situation that represents a system of linear equations. Write the system of equations and identify the solution. 1. Identify the input and output of each linear model. 2. Identify the slope and y-intercept of each linear model. And 3. Find the solution by setting the 2 linear functions equal to one another and solving for x, or find the point of intersection on a graph. Fitting linear models to data. A professor is attempting to identify trends among final exam scores. His class has a mixture of students, so he wonders if there is any relationship between age and final exam scores. One way for him to analyze the scores is by creating a diagram that relates the age of each student to the exam score received. In this section, we will examine one such diagram known as a scatter plot. Drawing and interpreting scatter plots. A scatter plot is a graph of plotted points that may show a relationship between 2 sets of data. If the relationship is from a linear model or a model that is nearly linear, the professor can draw conclusions using his knowledge of linear functions. Figure 1 shows a sample scatter plot, and notice this scatter plot does not indicate a linear relationship. The points do not appear to follow a trend, and in other words, there does not appear to be a relationship between the age of the student and the score on the final exam. Finding the line of best fit. Once we recognize a need for a linear function to model that data, the natural follow-up question is, what is that linear function? One way to approximate our linear function is to sketch the line that seems to best fit the data. Then we can extend the line until we can verify the y-intercept, and we can approximate the slope of the line by extending it until we can estimate the rise over run. Recognizing interpolation or extrapolation. While the data for most examples does not fall perfectly on the line, the equation is our best guess as to how the relationship will behave outside of the values for which we have data. We use a process known as interpolation when we predict a value inside the domain and range of the data. The process of extrapolation is used when we predict a value outside the domain and range of the data. Figure 4 compares the 2 processes for Cricket chirp data addressed in example 2. Interpolation and extrapolation. Different methods of making predictions are used to analyze data. The method of interpolation involves predicting a value inside the domain and/or range of data, and the method of extrapolation involves predicting a value outside the domain and/or range of the data. Model breakdown occurs at the point when the model no longer applies.